Hello, once again welcome to the solid state lectures. We have studied the dispersion relation in the case of crystals with a monoatomic basis and also with a diatomic basis. Then we found the heat capacity of solids or crystals, the Debye model as well as the Einstein model. So in all these discussions we have considered, or our discussion was based on the fact that vibrations in crystal are harmonic. That means the potential energy of the atoms or the particles associated is a quadratic function of the displacement from its mean position, from their mean position. So here our discussion was based on harmonic potential. That means potential energy is of the form Cx square, okay, where C is the force constant. So based on this, we have the displacement is the displacement of the particle will be harmonic. But many physical properties cannot be explained if we use a harmonic potential. For example, thermal expansion. Thermal expansion cannot be explained if we use harmonic potential for the atoms or molecules in crystal. Okay, so we have to adopt a anharmonic potential. That means we have to include the higher order terms for the potential energy, third order or fourth order terms in the potential energy. That means potential energy become anharmonic. So potential energy will have higher order terms Cx square minus some Gx cube minus F x raised to 4, etc. So this is called a anharmonic potential. Let us now explain the thermal conductivity. So consider a steady state flow of heat down along of temperature gradient dt by dx. Okay, T is the temperature, dt by dx is the temperature gradient of the solid, and then the current density, that means the flux of heat energy per unit time per unit area is given by minus kappa dt by dx. So this is here the thermal conductivity coefficient kappa is defined by means of this steady state flow. If the kappa is the thermal conductivity, then the flux of heat energy flowing per unit area of the rod per unit time is given by minus kappa into dt by dx. The current density of heat energy is a function of temperature gradient rather than temperature difference, suggests that the thermal energy transfer is a random process. That means the energy does not enter the specimen and transmit through the crystal without any deflection and reaches at the other end. Actually, the energy diffuses through the crystal with multiple collisions. So that is why the term dt by dx in the expression of the current density. By kinetic theory, the flux of particles along x direction is given by is given by 1 by 2 n times average Vx. Okay, so here we can write this in as mod Vx, average of modulus of Vx. Here n is the number density of particles or molecules, and Vx is the velocity of particles along x direction. We are taking the modulus of this velocity. That means we are taking the absolute value of the velocity. At equilibrium, there will be particles, the same kind of flux along the opposite direction, okay, of x-axis. Now, if small c is the heat capacity of per particle, heat capacity of a particle, okay. Well, heat capacity, you know what is heat capacity? It is the energy required to raise the temperature by unity. So if this small c is the heat capacity per particle, then if a particle moves from a point of temperature T plus delta T to a point with the temperature T in the crystal, then it lose energy of C into delta T. So delta T is the temperature difference between these 2 points. Then C into delta T is the total heat energy lost by the particle. Okay. In moving between 2 points of temperature difference delta T. Okay. Flux of particle in x direction is given by half n into average of modulus of Vx, and if any of these particle move between 2 points of temperature difference delta T, it lose energy C delta T. If dt by dx is the temperature gradient in the solid along x direction, and if delta T is the temperature difference between two ends of a free path, that means, and the temperature difference is delta T between these two, okay, T plus delta T and T. So if delta T is the temperature difference, then we can write delta T as dt by dx into Lx. Here Lx is the distance between these 2 points. So this is the actually free path, okay, one of the free path along the x direction. So this can be written as dt by dx into Lx is equal to Vx, velocity of particle along x direction, into tau. Tau is the time taken for a free path. That means time between successive collisions. Therefore, this can be written as the total. This the flux of energy is heat energy is given by minus n Vx into, here we have considered both the direction of x-axis, C delta T, which is given by, which is equal to minus n Vx into C delta T is equal to C into delta T is Vx dt by dx into tau, okay, or the average flux is equal to minus n average Vx square into C into dt by dx into tau. From kinetic theory, we know Vx square is equal to Vy square is equal to Vz square is equal to, average of this thing will be equal to average V square divided by 3, 1/3 of V square, or V square is equal to Vx square plus Vy square plus Vz square. These are equal, that means it is equal to 3 Vx square. So Vx square is equal to V square by 3, average of square. So this can be written as minus n into average of V square divided by 3 into C tau into dt by dx minus n into C v into v tau dt by dx into 1 by 3 is that 1 by 3. Here this n into C, n is the number density of particle, C is the heat capacity of a particle, and we can see that we can say that this is equal to 1 by 3 into capital C. This is V, and V tau, V is the velocity of the particle, and tau is the average time between two collisions. Therefore V tau is equal to the mean free path into dt by dx. Okay, so this is the current density or the flux of heat energy per unit time per unit area of the rod. So 1 by 3 CVL into dt by dx. We know that J is equal to minus kappa into dt by dx. So from these two equations we can write that the current density is equal to 1/3 of CV into L. Here C is the heat capacity per unit volume. Unit volume of the specimen. V is the velocity of the particle, and L is the mean free path. Mean free path means the average distance between two successive collisions. Okay, so this is the thermal conductivity coefficient kappa. This was applied first by Debye in describing the thermal conductivity of dielectric solids, with the C as the heat capacity of phonons, V is the velocity of phonons, and L as the phonon mean free path. That's for now. We'll have more discussion on thermal properties of crystals in the next class.